Well, then, we are live for episode 44 of Space Rocks Uplink. And it's a really big occasion, actually. We're not terribly superstitious here on Space Rocks, but as Mark joins, he can certainly confirm. Mark, happy birthday.
Happy birthday to us indeed, yes. Good to celebrate an anniversary, a very strange one, of course. It's a year that many of us wish we hadn't had to live through, but at least we've been able to do something creative and productive, I think, in the last 365 days.
Indeed, just one revolution around the sun, and rather a lot of guests joining us as well. And while we aren't superstitious, it does feel quite momentous that we're joined by tonight's guest to kind of mark the occasion with, because I suppose what our guest is all about, and I suppose what we're going to get into, it kind of speaks to one of the most fundamental philosophical and scientific questions I think of all time, right?
Yeah, well, it's funny you just said sort of innocently one time around the sun. Well, which sun? Our sun, maybe, but there are plenty of other suns or stars out there, which, of course, for thousands, hundreds, tens of years, we felt must also possess planets like the planetary system we have of the 8 planets and all the other stuff, the moons and the comets and the asteroids. But it's actually only recently, in the last 25 years, 26 years, that we've discovered them, that we know that they exist. And this artist impression behind me this evening on my backdrop is that it's not real images of planets going around other stars, but each one of those are objects that we know exist. They go around another star, and we know their parameters. We know how big they are, for example, their radii, how much they weigh, so we know their densities. Perhaps we know something about them. Are they gas giant planets like Jupiter or Saturn? Are they planets like the Earth or Venus, terrestrial planets, rocky planets? And that all got kicked off in 1995 by Michel Mayor and our guest this evening, Didier Queloz, who was a student at the time. And they discovered the first bona fide exoplanet going around another star, a star called 51 Pegasi. And so the planet became very prosaically known as 51 Pegasi b. And that opened the doors, because what Didier and Michel found then led to an understanding of where planets could be found, the way you would find them, the techniques, and how to refine the techniques. And we'll get into that. We'll get into the details. Why did it take so long? I mean, in the end, they were found, and we found lots of them. But what was the trick, so to speak? And of course, that led to lots and lots of work in the scientific community, and culminated for Didier and Michel in 2019 with the awarding of the Nobel Prize in Physics. And this field now of exoplanets is one of the leading fields in astronomy. There's a lot of people in it. There's a lot of excitement in it.
Indeed, it's an exciting field and an exciting moment for all of us at Space Rocks, of course. And what a pleasure it is. And while he joins, I'm pretty sure people will be able to see the photograph which you took. Obviously, Mark, this isn't just someone in the field. From you, Phil. Yeah. How are you? Welcome to Space Rocks, and are you receiving?
Yeah, hello. Pleased to be with you.
Evening, Didier. Good to see you again.
Well, absolutely fantastic to have you joining us tonight. And I guess I have to start with a big, question, because of course it's hard not to stray into the realms of philosophy. While all this is about science, it begs some other questions as well. So, from your perspective, how close are we to discovering another Earth, another blue planet?
Well, it depends what we call another Earth. We already found quite some with Earth size or mass of the Earth, or some kind of similar irradiation that you get on the Earth. But if you really want to find what we call a true copy, or let's say a twin of the Earth, this is still missing. We still have not achieved this. It's because it's very difficult. We're working a lot on that. I'm pretty sure that it's just a matter of years right now, or maybe already there are people that did it and they're working on the paper right on that. So just to say that this is imminent, because we have the technology, we have all the background to do that, and anyway we have found so many planets, so we kind of know to find a planet.
So let me pitch in there and try to take people back to 1995 and what it is that you and Michelle did and what was strange about it, right? I mean, this idea of looking for Earth 1 astronomical unit away from a star like ours, that's not what you found at all. And many things have been found since, but that discovery was special because it opened up the parameter space of how we find planets, because it was an unexpected discovery. So talk us through that. You were a young guy at the time. You were a student.
Yeah, indeed.
I'm sorry to remind you of that.
No, but that's fine. I think this is fair to say that we. I mean, there are different kind of discoveries, and we. I mean, we went into this call of the big surprise. That was something that nobody was prepared for, including ourselves. I mean, at that time, the idea that you have planet orbiting other star was in a way in the air, because there is a lot of argument, which is physical argument, for which you can really expect a planet to be orbiting any stars, essentially. But people have been looking for that, and there is a fascinating long stories of false alarm, false announcement, false claim, and it go back to the 30s, where people believed they have found planet, and later on there was this claim, and so on and so on. So that was a kind of field which is more like a field that nobody really wanted to go because it's a minefield, and it's a dangerous topic here. So when we decided to do this new machinery, I think my supervisor at that time never said we're going to hunt for planet, Didier. He just said, well, let's build a machine and let's find anything we can find orbiting under the star. And you can have anything which is between a star and the planet, and there is kind of a weird object called brown dwarf. So at that time, that was really the idea, and that was a kind of a sensible approach. Well, what has happened there is the machinery that I was building as part of my PhD turned out to be a bit better that we first thought about it. We found a couple of tricks. We managed to implement new ideas, and then in '94 we decided that we should really try to do something new there and pick 100 stars-ish, bright stars around us, and try to look if you can find something orbiting these stars, including planet as well. But the kind of planet that we could have detected because of the technology and then the capability of the machine was the big ones. Let's think planet like Jupiter. So Jupiter is the big one in the solar system. So it's something that you can detect, we could detect. But the challenge with Jupiter is it takes a long time for Jupiter to go around the planet. And since we were not doing any picture, the way to pick up the planet was to look at the star and to keep observing or measuring, in that case, the velocity of that star, and to try to detect a tiny change of the velocity, because when you have a planet orbiting a star, it's changing a little bit the velocity of the star. And in the case of Jupiter, this changed the global pattern. Well, it's the orbit of Jupiter, which is more than 10 years. So when I started the program, I think my supervisor went in sabbatical in Hawaii and handed me the key of the machinery and told me, have fun, start the program. I was at the end of my PhD, so I was quite excited. I said, good, I'm going to get a lot of good data. I need that for the end of my work. And really, it went absolutely crazy. It was absolute madness because I started to observe a couple of stars, and one of them was the star 51 Peg. It's bright stars of the North Hemisphere, or not the brightest one, but certainly a star you can barely see with the eyes. And then I was observing that object, and one night after the other one, I think the value I was getting with the machinery didn't make any sense because it kept jumping on and off. I mean, it went up and it went down, and at that time, really my reaction was really to say, this is the end of my PhD. I think this machinery doesn't work. essentially, because this should not happen. You were supposed to build a very, very precise machinery that will give you some kind of a steady, accurate value there. And then I got a little bit obsessed when I saw the first data point. Of course, I was so scared to mention that to my PhD advisor, because that would be embarrassing at that time. And I essentially work to find out where is the bug into the data. So you can imagine a PhD students and end of his PhD time, they're like in a bubble. You believe the only thing that is important is your work, nothing else. So I get absolutely obsessed. I did what I could. I think anything I could imagine. And there is a point when you have to admit that you lose a battle in a sense that you can't find any way to explain that stuff. And something in the mind, there is a kind of confident building there. And you say, okay, so I try all what I could. It seems to be real. So if it's real, then it's a planet. And that was the way I thought about that. And that's the way I came up to a point predicting the variability. And I came up with this amazing conclusion that the planet was a bit like Jupiter. But there's a big but here. The time for the planet to go around the star, its orbit or its orbital period, was not 11 years. It was just 4 days. It means the distance between the planet and the star was about 20 times closer than the distance between the Earth and the sun. So you can imagine it's a kind of orbit where it's very hot. So it is what we call a hot Jupiter. So this kind of planet didn't make any sense. They were not thought by a theory. Nobody had imagined it would exist. And essentially it was an impossible planet. Well, you're young, you're crazy. You say, why not? And that's something that certainly is part of the game, because since you don't have too much knowledge, well, you can think about anything a bit crazy like that. And I sent at this time, it was a couple of months later after the first data. And this fax, it was the days when you could not include a PDF into an email at that time. You had to send a fax. I know, you know what I'm talking about, Mark?
Oh, I go back even way before that.
Yeah. Okay. And Michel has this very kind reaction. He answered right away. He said, oh, it's a bit weird, but yes, maybe. And well, he admitted way later that he never believed at all that stuff. And he was right, because it didn't make any sense. Of course, he came back a couple of months later. I showed him all what I did, and he had to admit that was after some time of discussing with him that there is no other explanation than that. And then we decided that because it's crazy, we had to wait a little bit until we observe it again in the summer. And that time he came with me, and we were very excited. We have what's called the predictions, and then the story. I think all the data points were exactly where they were expected. And at the end, I think Michel realized that, yes, that's a planet. And I think at that time, I just panicked, because I realized that that is a crazy discoveries. It's either absolutely wrong. In that case, that's the end of my career as a scientist before just started, or this is great. And there is a possibility that we may end up one day in Stockholm, and it actually happened.
No, come on! You didn't think that in '95. Yeah, you probably did, but anyway.
No, people said it right away.
I remember.
Yeah, and I realized that this is also crazy, because I think, what else after that? I mean, you barely start your research, you barely start your work as a scientist, and you will never do better.
Yeah.
So I went.
So it's like winning the World Cup when you're 18, right? And then what the hell do you do after that, right?
So that was a bit crazy. And then, of course, I was still scared that there must have been a mistake somewhere else. So I mean, frankly, I must admit, the first years after the announcement was not a very nice time for me, because I always felt I was so awkward. I was not really at the right time, at the right place. And it took me years really to digest that. Well, on the top of that, the community was trying to fight against that, and nobody essentially believed that until 99, when we had other observation like an orbit, a transit, and then things cooled down, and then everything became obvious. So that was the story of the first planet. And why this planet, was so strange, because we don't have a hot Jupiter in the solar system. And the people, they are building modeling of this kind of planet. They assume that to reach such a big gigantic planet like a Jupiter, you have to be far away because you need to get a lot of icy element gluing together, and that it's impossible to do it next to the star. Yeah. So in the meantime, we learned that maybe we were a bit narrow-minded, and we just forgot some other physical ingredient in the formation of the planet. And it's a bit like if you are into your garden and you spend your whole life in your garden and you only have one flower, and then one day you decide to travel out and to go to another country, or you go to another hemisphere, and you realize there's plenty of other flowers and trees. And that's exactly what happened here. Yeah. We had this very anthropocentric perspective, and we were too much expecting a solar system like our own. I know we know, and there is one thing that we've learned is amongst the many planets that has been found. I mean, most of them, they look really awkward and very different from the solar system.
Yeah. So let me, before I hand back to Alex, just so that, because as we go through, it's sort of interesting to talk about the stages we've been through. So that first technique that you used, and of course is still used intensely, the radial velocity technique. This is where the star, again, as you said, the Earth doesn't just go around the sun. They both move around a common center of motion. And in the solar system case, even Jupiter, its big thing, that common center of motion for Jupiter and the sun is actually inside the sun. But the sun wobbles, moves backwards and forwards. And if you're in the right angle, you can see that, because it kind of gets a little redder as it moves away from you, a bit bluer as it moves towards you. And so that's that technique. And you've been refining that technique. So you've pushed these machines down that you can see much smaller objects, right?
Yeah.
And that's on the big telescopes in Chile and elsewhere. So that's still a really key technique. It hasn't gone away.
No, it's still being worked, and actually that is right now one of the very few techniques that can really aim at this Earth twin planet, because we have the technology right now. We've learned so much. We have improved by a factor 100 the capability of this machinery from the very early prototype, which is kind of classical in the early days of the science, because when you start really doing something new, there is so much to learn. So the kind of curve of growth of the knowledge is very, very steady to some point. Well, the surprise in this exoplanet business, it keeps being steady right now. It has no flatten out at all, because now we're talking about detecting life and so on. So it seems to be a crazy topic, and there's always something new and so much attraction, I think, for the big agencies, for the people to work into that. Yes, this is still one technique being used. We just have improved quite a lot, but that's not the only one, because there's other ways to detect planets.
So let's come back to transits and direct imaging and everything else in a little bit. So, but I'm conscious of trying to mix and match, because we have an audience who are certainly interested in the science, and we talk about the details there, but also the broader picture, how this fits in. And Alex is our man for those kind of questions.
Hey, well, there's so much to think about here. Obviously, the implications of that discovery are extreme, but when did you know? Because of course, I guarantee, just if it's a movie, right? You're looking through a gigantic brass telescope and you see something, and then you call the big phone. It's probably red, and you stab a number, and somebody reaches for the telephone, in the middle of the night, and that's how it all goes, right? So describe the moment you knew. Without a doubt, you knew for sure that it was what you thought it was. And it sounds like quite a lot of time elapsed between that moment and the moment you were willing to step out of the shadows and tell the world. Because of course there's got to be some hesitance. You said false alarms from as far back as the 30s. That's got to play into your psychology a little bit, right?
Yes, absolutely. It's a back and forth process that keeps going back and forth, because in a way, when you see something new, you're attracted by novelty, what you're seeing. And of course you start to try to extrapolate what is the consequence of that. But at some point you say, oh, hold on, back up a little bit. Maybe that is just something very simple that I do see. It doesn't mean that there is something amazing there. And then you back up a bit, and you go really in this kind of always a kind of, you oscillate between the two, and there is a moment when the oscillation can get a bit more into the one direction, because there is way more element you build up. Because you are at the limit of the knowledge, there is no truth. You are reaching a stage where you don't know what is the truth. The truth is just the data you're getting, and the data is so much at the limit. They are foggy, or you are half blind when you do that. So you have to kind of find out what it looks like, and you don't never really know exactly. So you have to look another way, and you have to try another way. So this is really this kind of game. It's like trying to solve a puzzle here, and you never had the full picture. So it's a process that you build on the basis as an evidence. I think if you want to, if there is a murder somewhere and you want to find out who killed this guy, and you have to build up evidence. And that's exactly the same kind of process here. You don't know first what to do, but you just see something is strange. So it's enough to try to understand what's going on. And this process takes time. Some of the field of physics, there is a well-known landscape, or there is a good understanding what to look, but it takes 100 years to find it. And we have had this amazing discovery, what we call gravitational waves, which was predicted almost 100 years ago. It's one of the main predictions from the Einstein gravitation theory. But because it's so difficult to detect, I think the people were aware, and there was some indirect evidence they would exist. But until you find it, it takes a long time to build up. And then at the end, you find what you expect. It was not exactly what they expected, but not very far. No, in our case, it's a complete different story. You don't have this background. You just find something awkward. And your task is to act as a scientist the most you can, and to try to come up with a series of rational facts. So if you want, it's not one moment when you call, you have plenty of moments. And for 1 hour, you are in a state of mind which is ecstatic. And then the hour later, you're absolutely depressed because you realize you forgot to consider that, and on and off, on and off, on and off. And I think this is what happened in any scientific discoveries. In the case when you really do something so, so strange, or that has the potential of having such a high impact, it's just there is high stake on game. But it's the same process. So instead of falling 402 meters, you're falling from 1,000 meters, and that's it. But you still fall.
So in this field, I'm going to be slightly cynical, because I think, I followed it as an outsider. I mean, I'm not too far away from it. I'm not a cosmologist, right? So I have some basis. And I knew Michel, of course, from the times when he was working with Antoine and working on binary stars and so on. So kind of technically I had a good feel. But it does seem to me that, for all that 99% of the work is positive, there have been moments where kind of people have overstepped the mark a little bit as well. Because, it's such a tempting field, right? The public love it, right? It's not only an amazing discovery in and of itself, but it has such resonance for the general public to say there are planets around other stars. Yeah. And, occasionally I've joked, that some people have gone a bit too far in their interpretation. So explain to us in a field like this, because I think for the public, how do we self-police? How do we actually kind of say, well, that person's put a paper out there, I don't think it's right, I'm going to put out my hypothesis. You've been in the middle of that for decades now.
Yeah.
Well,
I have my own views on that.
Yeah.
I'm not sure you're going to like it, but I have my own views on that. Well, to me, as a scientist, I feel I'm extremely emotional, and I think like all the scientists, I think scientists are very close to the artist on that aspect. Why would you do science? I mean, this looks a bit of an awkward activity, because I think you can't resist to look at things. You can't resist, you're a bit obsessed by things. So I think all scientists are absolutely highly emotional person. They may not be able to express it, so all of them, but I think this is still a very strong element. So the science is full of emotions, and sometimes it's difficult for people that are not doing science to feel it, because science looks very boring people in the lab, and they just too complicated, nobody understands what they're saying. But you know what I'm talking. I mean, go to a meeting about science, and you see the people are so emotional. They can be really aggressive, and you say, it's crazy, we're just talking about science. I mean, why is it so mad like that? So I think there is this element there, and it's very easy when you do something, because you have been working on something, to make a couple of extra steps. Well, some feel it doesn't matter because nobody cares. Yeah. But some feel it has a lot of impact, because the few steps you're going to do will be relayed by the media, because this is cool stuff to relay. So the media will always take anything they can, because that's part of the game, in trying to get to get visible and to try to convey this kind of element. So you're perfectly right. Sometimes the way to communicate science results, it's a bit too much, because the results say something, but at the end you sell it like, it's a bit like you buy a kind of a car, and then you sell it like a Ferrari or whatever. I mean, because it's still a car, but come on, this is not the same car you're talking about. So of course it happened, but to me it doesn't matter. It doesn't matter because science has this process of kind of let's say self-correcting itself, because sooner or later, if you're wrong, well, you will be wrong. That's pretty clear, because something will come and will demonstrate you've said a bit too much. But anyway, to communicate that to the public 24 hours later, they will have forgot what you're talking about, but they will have remembered that there are cool stuff going on in science, and maybe that would be attractive for them, and they may discuss them with their kids and say, oh, science looks cool, so why don't you do science? So I think it doesn't matter very much. We just have to be careful not to be too wrong. But if you're a little bit too much, I think it's okay. So I can live with a little bit of excess of emotion and scientists trying to tell way too much and trying to oversell. And that's clear when you're dealing with planet, and then there's all this question of life. And when you look back at the first announcement of exoplanet, and you see that some media have almost decided that some of the planet would have the kind of a flying kind of bird, or I don't know what it was. It was a kind of, I don't remember. It was kind of fish, flying fish. I can't remember. So it's just crazy, because there's nothing can say about that. But okay, it's part of this emotional element, and it's part of the dream about that. So why not dreaming a little bit?
Yeah. Look, I definitely agree. I mean, I think that excitement transmits itself, but it can go occasionally a little bit too far. Imagine, I mean, in the planetary sciences, how many times have we discovered water on Mars now, right? I mean, and it's like every time, hey, water on Mars. I mean, we know it's there, but I worry a little bit occasionally that the danger is that people kind of say, hey, you've discovered it 20 times, right? I mean, stop telling me. You must be making it up.
Yeah, I love that questions, because it's becoming a joke in the community that is finding a lot of planet. I think we must have announced at least 20 times the first Earth-like planet or something like that. And every time I keep telling, no, we cannot do that, because the media, they will realize, no, they don't care. They just relay it, and they believe it's very fun. And they always ask, what is a bit different this time? I say, yeah, there is a little bit something different here, and everybody is happy with that. So I think it looks like a bit of a common game, and it's part of the show. So, well, come on. I mean, Hollywood is always doing that. Well, we're doing a little bit of Hollywood movies, and we can do that.
Yeah. I mean, I have this joke, the titles were getting to the point where I was going to write a paper like, the first green exoplanet discovered on a Thursday spinning backwards or something. I mean, there's got to be.
Yeah, exactly. Yeah.
but yeah. So Alex, bring us back to the real world.
Well, it's wonderful stuff. I just want to echo the sentiment. We have people watching from all over the world, from France, from India, from Germany. The list goes on. Catherine said her mind's blown by the idea of a hot Jupiter that goes around the planet, a sun in 4 days, because it's so hard to conceptualize. Now,
yes.
I mean, there's one thing that I've learned on this journey in space rocks is that it's like the more we discover, the weirder it gets. It's almost like we're just learning more about how much more we have to learn, as opposed to just acquiring knowledge. It's almost just like it is just so unimaginable, and so on. And is there an implication that comes with these sorts of discoveries, though? Does it perhaps say something about the uniqueness or the rarity of our own world? I mean, are we at that point? Because I guess we're just at the beginning of this journey, but it does strike me that no one could have predicted what you've seen, but I guess what I do wonder about is, does it say something about the rarity of what we have right here on Earth?
Well, I mean, this is a difficult question. So, I mean, trying to conclude that something is rare means you have to find that stuff a little bit, but not too much, which means it's really difficult to find because it's very rare. so you are with it, and we're not there clearly now. What we have found is, I used to call that a gift of nature, because it turns out that this hot Jupiter compared to a planet like we have in in our own solar system, are ridiculously easy to detect, really easy to detect. And technically speaking, this planet could have been detected in the 50s by transit. They have the technology to do that. They just didn't imagine they would exist, but they could have done that. They could have designed an experiment to look at that, but nobody would have been crazy to spend money, and even I don't think they would have any chance to get the money for that, because it was just crazy. So I think what I'm trying to explain here is, because they are easy, we have been quite rapidly extremely successful. So this idea that there is plenty of planet is just because there is plenty of planet that turns out to be way more easy to detect with the technology we're using, that the one on the solar systems. And we have no a kind of, let's call it preliminary result, that certainly the majority of the planet are different from the solar system, in the sense they are orbiting much closer. Well, you have to imagine, you have the solar system, you have Mercury, which is the closest planet from the sun. Well, almost the 90% or 95% of all the planet that we have detected would fit within the orbit of Mercury. So they are really on a very short period. And when you do the statistical analysis, because they're easier to find, so you have to kind of correct from the fact that it's easy to find. So it doesn't mean that it's frequent. It just means that you have all the equipment to find them and not the right equipment to find the others. You realize that certainly more than half of the star, they do have such a planet. So we already can conclude today. So this kind of idea that we had, that all the planets would be similar to our own solar system, is not true. But it does not mean that we are rare. It just means that we are one amongst many. Now, to find how much we are, I mean, that's something that should come and will come in the next 20 years, because right now we kind of know to address that problem. We just need to do the job, and there is a lot of work, a lot of team along the world which is trying to get that done. And there is new a space mission that will be flown. There's a lot of program there, and then this question will be asked, and we may end up with something like, okay, maybe the chance to have a system like our own is 5-10%, or so. Would you qualify that as rare or not rare? I mean, we're just one amongst many. That's it.
Yeah. So you mentioned the transit word there. Let's jump to that, because of course that talks to the picture you have behind you, the Chaos mission launch.
Yeah.
At the end of
I was there in Peru.
It was my first launch, amazingly, but amazing. So the radial velocity technique is basically seeing the star moving through its Doppler shift.
Yeah.
But the transit technique is different.
Yes.
But as you say, it helps pick up the same systems in some way. So talk us through how that works and why that.
Yeah.
And as you say, we could have done it, in fact, if we had thought to look for those kinds of objects.
Yeah, the transit technique is fascinating, because I think it's a very simple scenario. I mean, this is similar to when you get an eclipse on the Earth, on the Moon, or the Moon on the Earth. It depends. This is exactly exactly the same kind of event. But in the case of a planet, it is only affecting a tiny bit of the light of the star. So you essentially look at the star, and if the planet turns out to just cross the star, it means the line of sight between you and the star, and then you have a little bit of a dip, of a blimp into the light of the stars, and this is called a transit. Now, the reason why transit was not really anticipated early on is because the chance of a transit depends on how far is the planet from its star. And if you consider a planet like the Earth, for example, I mean, the chance is less than 0.5%. It means you need at least 200 Earth-like system to have the chance that one would transit. And it looks to be...
So just to be clear, that's because if you've got a little thing and it's very close into the big thing, it doesn't really matter what angle it's at. It's going to cross over the disk of that big object.
Exactly.
But if it's far away, it's got to be perfectly aligned for you over there to see it. Because if it's slightly off, it never passes in front of the star.
If you practice archery, you know that it's easier to get very, very close to the target, not to be very far away if you want to aim at the center. That's exactly the same kind of concept. You have to be just perfect, otherwise you can just be a little bit. So it's exactly the same concept. So when we started picking up this hot Jupiter, and the fact that there are actually planets on very short orbit, then people started to realize, oh my God, it means the transit then should be quite common. So the chance of a transit of a hot Jupiter just goes up as 10%. So you need only 10 hot Jupiter and one will be transiting. And that's exactly what has happened. We kept detecting hot Jupiter early on, and then one day on one star, the famous star HD 209458, everybody on the early days know that stars, and it turns out to have a transit. And that was the end of the game in a sense, because when the transit was detected, nobody was arguing about these are real planets, because that was the end proof demonstrating that this was really the true explanation for planets.
I guess the key thing, for people to remember, I mean, it's on the order of 1% drop in the brightness of the star, but it happens repeatedly.
Yes.
And of course, a star could just have a flare or could dim, or a star spot.
Yeah.
But if it happens every 4 days,
exactly,
it's something going on.
Exactly. And that's the gift. And then the other gift is at that time, I mean, since the 70s, one space mission in US was in the mind of everybody, which was using the transit to detect the Earth. It's called Kepler. And when they realized that you could have short period planet, that was really a kind of a kickoff of these missions. And they managed to get the funding and to get everything in place. And then the mission got lucky, because practically they detected really thousands of transiting planets. All of them, or most of them, in short period, because actually, I mean, nature was so nice with us that they're only producing hot Jupiter, they're also producing hot Neptunes, hot Earth. The whole population of planet turned out to be very close. And the good story of that is the gift part of it. If this planet would have not existed, I mean, Kepler would have been a fiasco. They would have found almost no planet at all. So in that sense, the fact that we have this amazing, strange population that doesn't fit into a theoretical mindset to explain the planetary formations is the reason why the field has boomed in such a way that everybody started to go into that, because then you not only have a few planets here and there to study, you have thousands of planets, and then every planet looks to be different, and then you start to realize that how boring is the solar system, because you only have few to look at, and then you have an infinite number of planets, and you can realize that there's all the temperature, all the pressure, all the kind of atmosphere you can think about. So in a way, at that time, science did way better than any sci-fi book you can imagine, because all the planets we started to detect, I mean, in a way, went much beyond that any sci-fi description you can have on the planet you could imagine. And that was kind of a fun time.
So again, before I hand back to Alex, just so that everybody's aware, the key thing about the radial velocity technique and the transit technique is they measure different things about those planets. And that, of course, plays into what Cheops is sitting on top of that rocket behind you. So tell us again what radial velocity measures and then what transit measures, because they're not the same physical parameters. So when you get to all these densities and everything else, you've got to measure these two.
Yeah, that's true. So I still, we have not discussed really the physical nature of this planet. I just say we can detect them. So actually, when you do the radial velocity, well, you get the period of the planet, you get the kind of size, the shape of the orbit, and then you get the mass. You don't get exactly the mass. You get the projection of the mass, which is not very far from the true value of the mass of the planet. But when you get the transit, you don't get the mass at all, because what the transit does is to make a kind of a shadow over the stars. So what you have here practically is just to compare the size of the planet against the size of the star. Actually, what you have is the area of the planet, which is a shadow event, and you can use that, and you use the depth of the transit. We said transit is 1% blimp. 1% corresponds to actually a planet which is 10 times smaller than its star, and you get the size of the planet. And then, of course, you can combine the two techniques sometimes, and you get the transit and and the measurements of the Doppler shift, and then you get the mass and the size, give you the density. So having the density, you can disentangle a planet that is like Jupiter, which is very floppy, very light in terms of density of the water, or a planet like the Earth, which is a more heavier, denser planet, because it's essentially a planet made of silicate. So this is the trick, and actually you can do way more, because you can get also the atmosphere of the planet, because depending of the atmosphere, it changes a little bit the way the transit looks like. So there's really a lot of, I don't want to get into too much detail here, but there's a lot of tricks you can do there, in a way that we're not only detecting the planet, we're doing what's called exoplanetology. So we can remotely learn quite a lot about this planet. Even sometimes we can get even the wind on this planet. There is tricks to detect the kind of idea and the wind and the temperature of the planet.
Yeah, I mean, that's the one I want to get to, is, as I explained before you came on, these pictures behind me they're not pictures.
Yeah.
Nobody's taken a picture of a planet that resolves it, that sees the structure, but there's physics there. We know, as you say, a planet like Saturn is so light that it would float in water. And something like the Earth or Mercury, very dense, and you can measure those parameters without ever seeing the planet, so to speak.
Yes,
and exactly. I think that's that kind of leap that people need to be able to take, is, no, we haven't taken a picture of it, but we can know those things, and we can even know plausibly that they have rings or that they have moons.
Yes,
we can start measuring those things about those planets. Yeah. Anyway, Alex, so
no. I mean, it's just interesting you mentioned sci-fi, right? Because of course, the title of our uplink tonight is "Strange New Worlds." Taken from the famous mission statements of the Enterprise and Star Trek. To seek out, and of course, curiously, all the strange new worlds they find all look almost identical, very similar to the desert outside of Los Angeles with a different color filter. So there's nothing actually that strange about any of those worlds that depicted in Star Trek, which is always kind of ironic. But this is the thing, though. I mean, I think that what exoplanets have done is they stimulate the imagination, and obviously we immediately ask, how does it line up with the imagined worlds and so on? And there is something happening in the world of space exploration now that almost feels impossibly sci-fi. Great question coming in from the Hawk in Stafford in the UK. Yes, so how valuable will the James Webb Space Telescope be in furthering the study of exoplanets? Does it have implications, and what will
Oh yeah. I mean, James Webb Space Telescope is an interesting, I think, future satellite, because I mean, originally it was designed by people that didn't care at all about exoplanet, because at that time they thought, and they designed these telescopes, there were no exoplanet at all, and this telescope was seen as the ultimate machine to look at the very far part of the universe and to measure galaxies and that kind of stuff. And they designed this telescope for that purpose. And it happened something which is very rare in the space business, is along the way the telescope was built, the planets start to popping up. And people start to realize, but oh, hold on, I think we're going to fly this amazing new telescope in space, and you're not going to use it to the exoplanet? You must be kidding me there. And then something amazing happened. They start to retrofit the design. So when you do space business, you never do that, because you think your stuff you design and you do it. Well, in that case, they kind of try to twist a little bit the equipment, because then they had to do something completely crazy. And the telescope was designed to observe very faint object, and we were telling them, no, we're going to observe the brightest stars that we can see by the eyes, because what we want to do is we want to detect something about the planet. So yes, James Webb Space Telescope will be tremendously useful in the case of when you have a transiting planet. And the reason why it would be so useful, because you can use this capability of the transit to be slightly different depending on the color you observe your transit. It happens the same kind of event when you have the sunset and the sunrise. You see the skies change the color because of the trajectory of the light from the sun is affected by the nature or the physics interaction between the atmosphere and the wavelength you have. And it's exactly the same in the case of the planet. Actually, the planet doesn't have a fixed size if there is an atmosphere. If there is no atmosphere at all, well, there is a fixed size which is defined by the rock of the planet. But as soon as you have some atmosphere, then depending if you look the atmosphere of the planet into a kind of a color which is more sensitive, like the ozone, for example, and then the ozone is very far away. So in the case you would observe a transit of the Earth, in the ozone band, you will see the Earth much bigger. They will be about 100 kilometers bigger because the size of the atmosphere with the ozone about 50 kilometers away. So you can use that trick, but going in great detail during the transit. To do that, you need a big telescope, you need a lot of flux, and you need an exquisite stability during the measurement of the transit. And this is where James Webb will play a key role. And of course, people is very excited because they are really trying to get some kind of exciting molecule. One of them is water. We would like to detect water on the atmosphere of the planet. Water is quite common. There's everywhere water. It's a very simple element in the universe. But the question of the delivery of the water is very critical because you can have water when you form a planet. It doesn't mean it has to stay there. You can lose it and you have to bring it. So having some hint about the water, and then you can start dreaming about other gas which are maybe critical for the geophysics of the planet. And you can even dream some gas that could be a product of a life activity there. So this is where James Webb will be playing. So how far it will go, I think we will see. We may expect quite some big surprise from the James Webb Space missions about exoplanet discoveries.
Yeah. Just to clue everybody in, the launch, this is of course a NASA, ESA and Canadian Space Agency mission due for launch in October this year on Halloween. Telescope is currently being folded up and getting ready to go to French Guiana, where it gets launched, the same place in the background there. Exactly. On a bigger rocket, on the that's a Soyuz there, and James Webb will go on Ariane 5. And the results of the first open call for proposals just came out last week. So we now know how much of the first round of open time will be spent on exoplanets, and it's about 25%. So a quarter of the time, as you say, there was zero time when the mission started to be designed in the late 80s, early 90s, and then moving on into the 2000s. But again, you're absolutely right. I mean, it's the adaptability, the instruments have been changed, but the community's moved, and I'm sure we'll find the first observations maybe a bit messy, but over time people will learn to calibrate them extremely fast, because that's the thing in your business, right? It's not take a picture, there it is. It's all about understanding all of that noise and removing all of these weird subtle effects. And that's why you've been able to improve the technique so much over the years, because you've really learned. JWST will throw all these surprises at you because it'll have its own quirks.
We still have some nice picture, because in some case we have been able to take picture of planets. It's very rare, it's very extreme cases, because there are quite big telescopes on the ground, and there will be a new generation that will be definitely able to take picture of some of these planets, and then being very clever on the way you use this telescope, and essentially you kind of what's called deal with the atmosphere, because you don't like the atmosphere, it's not good for astronomers, and you can really stabilize and then the image in a way that you can really see something very tiny, very next to a very bright spot. And there are a couple of planets, and look, in the next 50 years there will be plenty of new tools and plenty of telescopes that will be detecting planets. So we're starting not by seeing them, but tomorrow we will start seeing more and more, and by seeing the planet we'll be able also to see the light that is emitted by the planet, and trying to study great more detail and what does it mean. So we're moving slowly to a stage by we're detecting and getting information on them without seeing it, with being blind, which is not a big deal for I think for science, because most of the stuff we're doing in science, we don't really see it. And that's right. The art of the science is trying to see behind what you can see by using sophisticated equipment. I mean, I challenge to ask the people working in the sun whether they have seen the boson. No, they don't see it, just detect it the same way. But they exist, and it's quite critical to understand the nature of matter. So this is kind of classic in science.
It's a funny thing you say that, though, because I think culturally astronomy draws people in because it does have that strong visual element, right? It is that you can go out and look at the stars, you can see the planets moving, you can have these beautiful pictures from Hubble and all the other telescopes. And so in some sense, I think it draws people over the threshold and say, I can see the universe. Although in fact, all these beautiful pictures of the Orion Nebula and so on, even if you stood next to the Orion Nebula, even if you went 500 parsecs and stood next to it, it would be just as faint and just as grey as it looks from here at Earth with the naked eye. It does not look anything like those pictures to the naked eye. So there's a little bit of trickery involved. There's no lies, it's amplification, enhancing things. But again, I think that's the thing that we suffer from a little bit in the field, is that everybody expects to see it because they can. In particle physics, nobody expects to see anything because there's nothing to see, right? And they've kind of adapted to that idea. It's all going to be data. With us, it's like, oh, there's a picture. Are these pictures behind me real? They look real. Somebody's done a good piece of art. And you know that, right? In the exoplanet field, there's always these artists' impressions of...
Yeah, and they're great. And we like them very much because this is really essential what they're doing.
Yeah,
that's where we are.
But occasionally you must have that question. You say, oh, well, it's amazing. Look at those pictures. Like, well, no, it isn't real, but the data are real, right? And that, making that leap.
Yeah, well, it's part of the science, part of communicating science, and I don't think it's a real issue. You can really in a way feel the beauty of the universe and the way you like. I mean, it could be just because you walk outside and you look at the galaxy and that's it. Or you can also try doing some picture and trying to play with filters to just see some. And this is fine. It's like if you want to study snow, well, nothing prevents you to do a beautiful picture of snowflakes because this is beautiful. I'm not sure you're going to learn really if there is an avalanche by doing that, but certainly you will have beautiful picture. So there's not one against the other one. I think it's perfectly acceptable to do both.
Yeah. Let me pick up before Alex comes back in again, because the one technique we haven't talked about, which of course I'm duty bound, it's in my contract to talk about, is when the Gaia data come out. Because of course Gaia is going to help us with this long period planet problem, right? So Gaia is this mission which measures the positions of stars very accurately. And if a planet's going around, again, the star's going to move. We're not going to see the planet, but we're going to see the star move around. Yeah. So what do you think? I mean, we haven't seen those data yet because you need a long time baseline with Gaia. It's been flying now for 8 years, and we'll start beginning to see 2 or 3 year planets like the Earth.
Yes.
So is that something which, I don't know, I'm asking the exoplanet guys, is that, oh yeah, we're past that now, we don't need that.
No, we never passed that. I mean, we take all the data we can. No, we love Gaia. I love Gaia. And that's just great. No, Gaia is fascinating because this is really the kind of techniques that everybody would have bet on. So this is really the technique that everybody say, oh yeah, Gaia is the way to do. And the people even write papers at the time before we made the announcement of 51 peg, because when you do the math, you realize in terms of techniques, if you can detect the motion on the sky, because what we're talking about here is really a motion, it's not anymore a change of motion, which is a speed. Then if you have a planet like Jupiter, I think there is a kind of huge motion, and this can be detected, and it's still challenging, but it's certainly something that seems feasible, and people were betting on that. They thought about doing this kind of program, and it never happened because at the end you really want to do that in a very comprehensive way, and you realize when you want to do a survey with tons of stars, it's not that difficult. And in that case, ESA has really a long-time expertise because they inherited from Hipparcos, and then they had this capability. So yes, Gaia is going to find planet, is going to find the kind of planet we have difficulty to detect right now, which is exactly this kind of Jupiter I'm talking about. So I'm pretty eager to see what Gaia will get here. Of course, Gaia will be limited this time by finding planet on very nearby stars, which is fine because this is where the amplification is the most visible. But we're getting to get additional data that we just can't get, and it would help to complete the picture. The picture is very complicated because depending on the technique you use, you're sensitive to that kind of planet or that kind of planet. But at the end, we want to have a comprehensive picture to understand what is called the planetary populations, and it's certainly a very good technique to find out planet orbiting very nearby stars. And we are really interested by nearby stars because they're nearby and they are very bright. So we can do a lot of stuff on these stars. Yes, I love Gaia. I'm really eager to see. And I always believe it takes too long to get this data. We want to see the data.
Well, look, it's because you come from a world where your planets go around in 4 days. Come on, look, our planet, these planets go around in 3 years. You've got to make them go around 3 times.
I know.
Believe them.
Well, you tend to, it's cool when the reality is just so unimaginable that it would be implausible if you had to write it, and I guess the question in the chat tonight with people that joined us from again all over the world, Colombia now, is so can we detect oxygen and methane? From Peter. He asked, what are we actually looking for if we're looking for something that's habitable? Just what does that mean? And I suppose perhaps that veers into the world of astrobiology, because of course our concept of what's habitable has expanded greatly over the last few years. But
Okay.
what are these signs?
Yeah,
What are we going to be looking for?
Yeah, okay. This is a great question because I'm spending a lot of time right now. So I don't really like the word astrobiology because I think it connects two things which may be too far apart. But I will explain what I have in mind here. So the first question is, can we detect molecules that mateins? And yes, of course we can. And there's plenty of molecules we can pick. It just depends on the amount of flux and the capability to resolve this kind of molecules through a transit or just by directly seeing the planet. So it's definitely something that we will be doing. Of course, when you're dealing with small, tiny atmosphere, there is little gas, so it means the signal will be tiny. And the more you want to look for that kind of molecules on a very small atmosphere like the one we have on Earth, the more it becomes difficult. But if you look at molecules on planets like Jupiter, I think we have already detected quite a lot of molecules, and including water on planet on other stars. And it's quite interesting that people are very eager to detect the famous water into the atmosphere of our own Jupiter, and so far failed because it has to go quite deep down into the atmosphere of Jupiter. And actually the detector didn't survive deep enough to be sensitive to the water, but the water has been detected on plenty of hot Jupiter for the simple reason when you compute where is supposed to be this water layer on a planet is essentially on the outskirts of our Jupiter. When on a Jupiter cold planet like we have, it's more deep inside. It's much more difficult because the pressure is higher. So just to tell you, we're detecting these molecules and we will keep detecting this molecule. The concept of habitability, it's kind of a strange concept because it builds on a very simplistic perspective, which is, well, what does it mean for a planet to be able to keep liquid water? And habitability is just telling a planet is able to keep liquid water. So by asking the question, you realize you are entering into a loop of plenty of other questions. And the next question is, well, it depends on the atmosphere of the planet, because depending on the atmosphere, you can end up with a completely different scenario for the water. But assuming you have an atmosphere which is not too different from the atmosphere of the Earth, then you can define a range. Essentially, if you get too close, you lose the water. If you get too far away, you froze the water. It's not anymore liquid. So this liquid water, I think, boundaries, it's called the habitable zone. And then you can twist it a little bit depending on the nature of the atmosphere. And it is understood as the minimum conditions if you want to imagine life, because everybody agrees, there's a few things everybody agree on about life is liquid water is certainly the easy way for life to just to do the chemistry, to make the chemistry working. So that is really what it means. And there's nothing else about that. No, what we have to be careful, and the step we should not be making, well, you could have life without detecting habitable water, because there is some planet where they can build water without being habitable. And if you pick, for example, some of the satellites of the giant planet, we know that some of them, they have liquid. Is it water? We're not really sure exactly what it is, but certainly there is a way to get water in. And the fact you have liquid water doesn't tell you anything about life. So the question of life is a way more complicated question. And actually, it depends quite a lot about what you understand about life. And I'm afraid all the program that is started in the 70s, that is in a way inherited from the first Martian missions, they created this field called astrobiology, which is trying to connect the biology of life on Earth and project it into space. But all what they did is trying to push the boundary in terms of temperature, pressure of the life as we know it. I'm not sure it says anything, and actually we have not learned anything about the origin of life during the last 50 years until quite recently, but not from the astrobiology perspective. It came from the chemists, and it came from the chemists using computers, because they started to play a lot of network of reactions from the molecular biology, molecular chemistry, and they realized that there is maybe a chain of reaction that can produce what's called the starting element for life. One of them is the amino acids, if you want to explain why there is amino acid. And then you can imagine mechanism when you start from the amino acid and you build more complex molecule that sooner or later becoming gradually independent from this external environment and get more and more life. We're not yet completely into this past, but the progress made in the last 5 years has been quite tremendous. And the fact we're going to go on Mars and going to get some imprint of the early, let's call it chemistry at the surface of the planet, may tell us something about possibly some kind of prebiotic element there. I'm not talking about life here, I'm talking some chemistry of life, because we know that Mars early on, essentially the first billion years old, was quite similar to the Earth. And we know that life on Earth already was started at that time. So there's an expectation that there may be something like a kind of an imprint of a milestone of that time scale that has completely been erased on Earth because of the plate tectonic is still visible on Mars. So this is a very exciting topic. I think we have been very naive in the past, but I think right now there is a serious chance that we will be making progress. What does it mean in terms of a capability that we'll have to produce life into lab or to remotely detect life? I don't know, but I can tell you the topic is so exciting that we're going to try. We're going to try very hard.
I mean, just a couple of comments there. I think, this point that you made that just because we find life in extreme locations on the Earth, that tells you that life is adaptable. It doesn't necessarily tell you where it formed and whether the preconditions for life forming are met elsewhere. So saying, microbes on the Earth could survive on Mars, that doesn't tell you anything about whether they could have formed on Mars.
Yeah.
So I think that's a really important thing which people need to realize. And it's, as you say, it's a bias that's built in. The other thing, so I mean, of course, it comes back to your earlier point about teasing out signals and coming backwards and forwards. So the example people will have heard of in the last year or so, of course, is the putative detection of phosphine in the atmosphere of Venus.
Yes.
And what that meant, right? It's a non-equilibrium chemistry. It can only exist because these processes, well, maybe not. Maybe other processes can make it. But it was that, I think that's a really important lesson. If we find life somewhere else, it won't be a eureka moment. It's not probably an alien walking across the picture and saying hello. It'll be debated endlessly for years because somebody, as they did with the first planet, will say, Didier, you're wrong. I've got a model which proves you wrong. Yeah. And then, because the detection will be so at the margin, either because the planet's so far away from us or because the molecules have so degraded, you're piecing things together. So I think that's an important lesson for science as well. People shouldn't expect, unless the aliens land on your lawn tomorrow morning and say, we're taking all Nobel Prize winners away. Enough of that,
Yeah, I mean, this is exactly the point. You're right. I mean, when I got the question, when exactly do we know for certain that there will be life? Well, it's either there is life on Mars and we're going to dig it out and see it. So we're going to see something cramping and moving around, or we have to wait that an alien land on our land. That's it. That's the only way. Otherwise, it will be a very gradual process, and we'll have hints and bits and there, and that's it. We have to live with that for a long time. Yeah. But I think it's an exhilarating prospect to do that because it's
I completely agree. But it's that science communication interface again, isn't it? Just yesterday, take the example of the muon G-2 experiment.
Yes.
New physics. It's new physics because actually it's very exciting from a physics perspective. They've refined, they're getting close to the 5 sigma detection. It's nothing new. It was already there as an anomaly. And one group says, actually, we can explain it, another doesn't. But the newspapers today, new physics. It's like, whoa, well, hold on. That's not quite how it works. But it's important that we educate, not educate, that sounds too much. That we engage the public so that they understand the process we're going through. It's not literally the eureka moment sitting in a bathtub going, hey, I've displaced the water. I've made a discovery. It doesn't usually work like that, right?
No, I've seen it in movies. That's exactly how it works, Mark. It's always but I have to ask you, perhaps on that note, just like in terms of your own biography, and your own discovery. You mentioned sci-fi. Describe your own journey into all this. What was the moment that you were inspired to follow this field of study? I think some of the people watching and myself would be fascinated to know where your journey began.
Yeah, I think how I ended up like that. Well, I think it's because I'm just so curious. I never had enough, and I was very, very curious. I always wanted to understand things, and since I was kind of gifted in mathematics, I decided physics would be the kind of a king of the science, which is not true. Don't believe that, but that was my mental picture, and I said I'm going to go physics because I will understand everything. Then I realized that the more I was learning physics, the less I would understand because more complicated it became, and then on and on. And I realized that doing research would be a way to just use my skill, and I can see myself in trying to feed this curiosity as a living. And I'm fortunate because I can make a living with that, which is just amazing when you think about it, because I get the feeling I'm working at all. I just get the feeling I'm expressing my curiosity and trying to feed my curiosity. And I still have the same curiosity. It has not changed. And this is very scary because you could expect that by the time it goes down. No, it's exactly the same. I'm curious about anything. And I went into physics and then astrophysics because, well, it was cool. I mean, black hole, beginning of the universe, kind of cool stuff. I mean, you want to understand what is this general relativity. I mean, how come the time is not something absolute? I mean, all this idea, I thought it was really super cool. And I went into that when I saw some telescope from picture in Chile on the top of volcano in Hawaii. I said, wow, this is really great. We can work there. Oh yeah, I'm gonna go there. And then and then on and on, and then the idea to have a satellite. I think it's just crazy to imagine you build something and it keeps rotating on the orbit there. So this is what it is. And so I realized I managed to make a living just by playing with my curiosity and trying to use it to get this energy and to keep doing things. That's it. Nothing really special. I don't think I expect to get really a lot of answer, but I love asking questions for sure.
So Alex has just communicated to me that we said it would be an hour. I'm happy to go on if you've got a few more.
Yeah,
minutes.
We can continue 10 minutes. So
I just wanted to ask you a couple of specific questions. So firstly, let's talk about the thing that's behind you there, the KOPS mission, because this is not only special for the exoplanet community, but it's also because you're a Swiss national, you work in the UK at Cambridge, you work in Geneva, but this is a big deal for Switzerland, right? KOPS, because it's a partnership between ESA, Switzerland, and a consortium of other countries. So tell us what's special, because it's a relatively small satellite. It's not JWST.
No.
It's built fairly quickly, but it does a key thing, which is important, I think.
Yeah, well, I think the story of KOPS is pretty cool because I used to be a ski instructor. I'm Swiss, so and every time I see my colleagues Andrew from St. Andrews, and he loves skiing with me, so he went to Switzerland and we went skiing a day, and it was a time when we were trying to think, what do we need? I mean, to really do better. And at that time, we were doing the Super WASP experiment, all this transit, and we were a little bit depressed because it was at the time when Eddington was dead, and the Eddington story. And we wanted
to be clear, this is not Eddington the scientist; it's Eddington the satellite.
Yes, satellite. Sorry, Eddington the satellite.
Been dead for quite a long time.
This is one of this ESA mission that was decided and then cancelled later on. So and then we say, but maybe I think what is needed is really some kind of agile, small size satellite, about 30 centimeter size, that is able to point specific target, but with an extreme accuracy to get the detailed transit. And we realized it was missing into the global grand scheme, all the equipment. And we said, well, let's try to do that. It's amazing because we were designing this in our head and skiing, and it was very high. It was in Chamonix, and we had a great day. And it becomes so serious. So when he went back, he said, okay, I'm going to do my stuff in UK, trying to find some funding. He did a bit of work in UK. And then I was in Switzerland at that time. I said, I'm going to find some stuff and to do some study. And I went talking with my colleague in Bern, which is Willy Benz, which is, Bern is known to build space equipment. And I spent some time to explain the concept. And Willy said, this is amazing. We have to do it. We have to do it. And I think we spent a couple of years to convince the Swiss industry that have the capability, because Switzerland have definitely the knowledge, the capability to just do it, because they were just afraid. They were just too Swiss in a way. They say, oh, no, if you do that, it's too complicated. We're going to lose money and so on. I say, no, guys, this is amazing. You're going to demonstrate your skill. And then we got lucky, because after banging the door of these people, one of the CEOs say, okay, we should do it because it's so cool. And then off we go. And then we got lucky because ESA had this announcement and on and on. And at the end, we were able to design this satellite in a record time because it was a very cheap satellite compared to other satellites. It has to be built very, very quick, which is something that ESA never do actually. So we had to cut a lot of corners and we get a lot of trouble with ESA because of this. But at the end, it was successful. So we launched it.
Bad guys, we still have a dartboard.
Yeah, we know.
Your picture and Willie's picture. We throw darts at it.
We were so much the black sheep, so they never dare doing another mission of that class. And I do regret that. I do regret that because it's quite a success. I
don't think it's quite as simple as that. But yeah, you're right. It needed a new model making, that's for sure. And of course, when you make new ways of doing things. But
so the idea was to get very exquisite transit, and by this you can learn. I think you can constrain really the true density of the planet. You can learn if there is some ring and something. And then we got lucky also here, because another space mission was launched about at the same time, which is doing kind of a survey, which is panning the blue sky, but it's much tiny telescopes. And actually it's called TESS, and TESS is providing tons of great target for CURBS. So no, the team TESS and CURBS they are really like twins, and they're working together, and we're doing a lot of great discoveries and with a very, very exquisite definition of parameters of planets.
So the launch took place in December 2019.
Yes,
we were there in Kourou, and that was great to see. We went out to the launch pad once, and at 5 o'clock in the morning, didn't launch.
Yes.
We had to do it the next day again. And it's been producing science results. Those have been fed from the science team through Kate Isaac, who's our project scientist,
yes,
to me. I cover them. People are really, really excited. But of course, let's talk about the future just briefly. We have Plato, which is
yes,
kind of ESA's
yes,
big version.
That was a big version of TESS, yes.
Finding lots of planets transiting, going around nearby stars. And the fact that they're nearby is important because then you can do all the other follow-up observations, right? Yes. And then beyond that, we have Aerial, which is going to be able to look for the atmospheres. So doing kind of more of JWST because it's more dedicated to that. But I wanted to ask you a final question. And, we've known each other a long time. And people will be shocked by this question. But
my God.
But I know you'll take it in the right spirit. So the model of science, which is this kind of old school model, which, great men win big prizes and go to Stockholm and wear bow ties and get prizes. It's not really how science is done mostly these days, right? So you're in that kind of weird position. You're a Nobel Prize winner. You're kind of, in a way, you've got a foot in the past of the way the great men of science were. Very rarely great women, right? And let's be honest.
Yeah.
But now you've got the other foot completely in the modern world where there's huge teams of people, and this idea of recognizing one over the other seems a bit weird, right? Now, for what you and Michel did, that was 1995. But since then, it's all been about team building.
Yes.
So give us a bit of an impression about that, because I think people, again, in the public domain, they look up to Nobel Prize winners for obvious, you don't win it without having done something great, but it's much more than that. It's like Formula One. It's not just Lewis Hamilton or Ayrton Senna. It's about all of the people behind. So just give us a couple of minutes how
I'm very pleased of this question. So science is a construction. So the science you do it because people have done something before you, and they have been successful because people have been doing before you. So it's a big chain of knowledge which is being built. So every scientist inherits from the scientists from the past, and has the task to deliver and to make sure that they will give the stick, to the next scientist, to the future generation of scientists. So this is really a responsibility. So I see the science as a monster building that we're all building, and each of the scientists bringing a little bit of a piece of stone. So some people, they got a bit more lucky, they got a bit more inspired, and they are bringing bigger stone. But altogether, one stone has a meaning because there is plenty of other stones. So I really see myself like that. No, there is plenty of prize. The Nobel Prize is something extremely visible. I think I understand the principle that there is certainly a lot of scientists that would certainly deserve a Nobel Prize, and certainly scientists that would deserve more than me a Nobel Prize. So there's certainly no doubt about that, because there's a lot of great work, and there's a limited number of Nobel Prize of physics every year, which is 3. That's it. So this is really what it is, and this is a bottleneck, which is not very fair. But once you understand the visibility you have as a Nobel Prize, I feel pretty much okay, and I like very much the idea, even if it's a little bit unfair, because I don't see why we're talking so much about people that are just playing football and other people that just appear many times, playing in a movie. That is, I don't feel they deserve more than me as a scientist. So I'm glad that we have the same mechanism in science to promote some people, even if it's unfair. But what we would expect, and that's something I feel very strongly, I think we have a responsibility than the scientists, is to really use this echo chamber. Well, first to communicate what you do, but it's also to engage with the public and to not be shy to answer the questions with your heart, with your soul, with the way you understand science and your experience. Try just to communicate. And I think we need big prize, because whatever happened, I think it's impossible to talk about tons of people. You need some people that are placeholder. You need some people to hold the flag, and that's what it is. And I think the prize are meant for that. So we should continue this prize, and we should have many of the prize, not the only one. There's a couple of big prize, and then everybody getting that kind of prize and should feel responsible. And that's why when I got your invitation, I say, of course I do that. And I'm accepting a lot of invitations like that, because I really want to have a chance for people to talk to me. And I keep doing that as much as I can, because I think this is responsibility.
Fantastic.
I will get trouble with a footballer.
Well, I tell you what, we'll invite you on with some of those celebrity actors that we have on, and you could say, sorry, how much are you getting paid per film? How much do I win from that? You can ask them that question.
Well, I can't think of a better summation of why Space Rocks exists, or why I think Mark and I, have spent the last year doing Uplink, because of course this is the first anniversary of this particular collaboration. It's that very thing. It's that celebration. I say, on behalf of everybody who's been watching tonight, everybody at Space Rocks, thank you so much for joining us. We have more people joining from the Ukraine, from Lithuania, from Finland. The list goes on and on. And it's all about this sharing of ideas. So thank you so much for your time. And I really hope it won't be the last time, because I feel like we only just got started.
Yeah.
Thank you.
Yeah. Look, Didier, it's great to see you again. And thank you very much. I think the one thing, you said it at the beginning and you demonstrated throughout the whole thing, science is emotional, right? It's an enthusiasm which people have. And as you say, not everybody can express it, but it's bottled up inside, right? And it's the moment when, as a scientist, you realize you're just doing a job, that then you need to go out, walk around the countryside, go and dig a hole somewhere and find something interesting. I don't mean to put yourself in it, no. So, find something interesting, because that's how we became scientists, right? Yeah. Is through that curiosity. But one thing we have to do right at the end, it's just a tradition in Space Rocks Uplink, so I'm afraid there's no escaping, is we have to link the two things. We have a hand signal. So this is a test. Who can do the Vulcan salute, live long and prosper? So you have to try that one.
Oh my God, I can do that.
So live long and prosper, and then rocks, space and rocks.
This is okay. This one, I know it.
All right. So we would love to have you come to one of our physical events and speak to the public. We of course, we're waiting for coronavirus to end. Yeah. We'll be doing events around Europe when that's all over, and we'd just love to have you along. So thank you very much for coming. It's been fantastic.
Thank you. Thank you, guys.
Thanks very much. Bye, Didier. Talk to you soon. Bye-bye.
Well then, Mark, suitably mind-blowing, and what a great way to mark a year of doing Uplink. I think we should keep doing these. What do you think?
Yeah, I think so. I had this utterly cheesy thing earlier on. I was thinking of Christmas and thinking of the song, not the first Noel, but the first Nobel. Well, we know some other Nobel Prize winners, so we'll drag them on. It'll be good. But it's not all about that. And as Didier said, there are the sort of the standard bearers who get to be right out in front of the media and use that responsibility. But there's so many interesting stories about, from the engineers, the scientists, the astronauts, and the musicians, and the cultural side. And we've learned in the last year that that's a fantastic mix. So yeah, let's definitely keep going. And with that in mind, we will not be back next week. We are going to take another break for a week, but we will be back the week after, won't we?
Indeed. Just well, let's just say plans are afoot, and you're going to be one to watch this space, because well, I mean, let's just say it's exciting, Mark. It's exciting.
Yeah, it's a big one. I mean, it's partly we need the time to prepare as well. So it's going to be a special day and a special episode, and there's lots of work will go into it, but you really won't want to miss it. So do join us in a couple of weeks.
Indeed. Anyone watching, the full details for our newsletter, our mission updates, which we send out ahead of these, are available. Please sign up so we can stay in touch with you. We'd love hearing from you. And Mark, we'll see you again in a couple of weeks.
Thank you very much, everybody. Good evening. Bye-bye.